Today we're going to look at material for exam 6. And your textbook is chapter 15. We're going to talk about solutions. Now we've discussed stoichiometry for situations where you have principally solids reacting with one another. So we've been able to write the chemical equations and use those equations to solve problems in stoichiometry. Today, we're going to take that another step and look at stoichiometry where solutions are involved. And not just that, but define how we deal with solutions. How do we define solutions? And how do we quantify them so that we can use them to do stoichiometry? Right? So those are the topics, and they're just there for any purpose you wish. So what is a solution? Early in the semester, we defined a solution as a homogeneous mixture. And that definition hasn't changed. But now we want to include information that will allow us to quantify the composition of a solution. And the first of those is the solvent. The solvent is typically the largest amount present in the solution. It's like the carrier, and everything else is carried by that solvent. There are some exceptions. For instance, if you prepare sugar water for your hummingbird feeder, you're probably going to add equal volumes of water and sugar. But it doesn't have to stop there. Sugar is so soluble in water that you can continue to add sugar to the point that there's more sugar in the solution than there is water. But we still consider the solvent water because it started out as the major component, and we consider it the solvent no matter how concentrated the solution becomes. And there's always just one solvent. Then everything else that you find in that solution, in that homogeneous mixture, is the solute. And these can be many. Can be 1, 2, 3, as many as you want, or as many as will enter into the solution. Now, aqueous solutions are ones in which the solvent is water. And we use a phase designation of AQ for aqueous solutions. Now, as a matter of fact, any homogeneous mixture can be considered a solution. And you can have various mixtures of different phases that are present in the solution. For instance, the first one in our table is example is air. We're breathing in a solution every day, and that air is a solution of multiple gases. Now, how do we define that solution? Well, the atmosphere kind of deviates from our definition, but we can force it to obey the rules when we consider that air is about 79% nitrogen and about 21% oxygen. There are other gases in there, but these are the major components. So nitrogen would be the solvent, and oxygen would be one of the solutes. But this is a situation where you have gases mixed in gases. And the final state of the solution is still a gas. Now, we're most accustomed to solutions that are in the liquid state. But they can have, we can introduce different solutes into that liquid state. And the solutes can either be liquid or solid to start with, or they can be gases. That the one where we have antifreeze in water, antifreeze is ethylene glycol. And we put it in water because at higher concentrations, it causes the freezing point of water to go way down, and the boiling point of water, of the solution, that is, the solution will increase to a very high level. That way, you can put this solution into your radiators, and the engine will become hotter than 100 degrees Celsius, but the solution will not boil. Or in the winter, the temperatures can drop well below 0 degrees Celsius, and the solution in your engine will not freeze, and as a consequence, rupture different parts of your engine. So that is a case where you put a liquid together with a liquid, and you end up with a solution that is a liquid. We can dissolve a gas in a liquid. Carbon dioxide dissolved in gas gives us pop. And the solution is in a liquid state, but there's gas dissolved as a solute in that solvent. We most typically think of solutions as a solid dissolved in a liquid, such as the previous example of a sugar dissolved in water, or salt dissolved in water in seawater. But you can also have solutions that are made of two or more solids. Brass is a good example. Right? Brass has at least copper as the solvent, and then nickel as one of the solutes. Now you can have other solutes in there, but these are the major components. This is the major component of the solvent, and then the next most abundant component is nickel. So there you have a solid dissolved in a solid that makes a solid. Now, of course, you can't just put a chunk of copper and a chunk of nickel, push them together and make a solution. It doesn't work that way. They have to be melted. They have to be in the liquid state so they can dissolve in one another. And then when they cool, they become a solid. And now you have a solid solution. Now, there's another concept that we have to deal with solutions, is the solubility. Solubility simply means equals the amount, I should say the maximum amount of solute that will dissolve in a given amount of solvent. Okay, that's defined as the solubility. So once you exceed that amount at a given temperature, I should put that in here also. At a given temperature, the amount that will dissolve in there, if you exceed that amount, then you will have the solute will remain undissolved. In other words, for instance, if you try to dissolve a solid, say sodium chloride as our example, in water, a certain amount of sodium chloride will go into solution, but if you exceed that amount, then the rest of it will lay as a solid on the bottom of the beaker, will not go into solution. Now, in this example, we see that a solid is dissolved in a liquid and produces a liquid. Now, for sugar, the sugar remains intact as a molecule in the solution. But for ionic solids, when they go into solution, they break apart into their individual ions. And in this case, the sodium chloride breaks apart into sodium ions and chloride ions. And they're surrounded by water molecules that keeps them in solution. Now, for most ionic solids that are placed in solution, when they break apart into their ions, they are particularly attracted to the solvent molecules if the solvent molecules are polar. And water is an example of a polar solvent. Water has a shape like this, and the bonds, these are covalent bonds. The bonds between the oxygen and the hydrogen is where they share electrons, but they don't share equally. In other words, oxygen has a much stronger attraction for the electrons. So we say this bond is polar. In other words, this is the slightly positive end, and this is the slightly negative end. And we do the same thing for this bond over here. Well, what that does for the molecule is it makes the overall polarity of the molecule slightly negative on one side and slightly positive on the other. Now, I say slightly because water does not ionize in this fashion. It simply has an uneven distribution of electric charge in the molecule. So that gives you an overall positive side to the molecule and an overall negative side to the molecule. And that makes it particularly attractive to ionic solids. So when sodium chloride goes into solution, the sodium is surrounded by water molecules like this. Because that's negative, you get an electrostatic attraction between the sodium and the oxygen of the water molecules, and they surround it in 3 dimensions. Whereas the chlorides are negative, they're going to be attracted to the positive side of the molecule. And that keeps them in solution. Now, when the solid sodium chloride crystal, which is in the shape of a cube, is introduced to the solvent water, those water molecules are attracted to the surface of the crystal, as shown here. And the water molecules are still being attracted to other water molecules, like this. right? They're still attracted. And these, all these water molecules out here apply a force against the water molecules that are being attracted to the sodium or the chlorine in the sodium chloride cube. And that force is strong enough to remove ions from the cube. They supply enough energy to remove those ions, and then once they're free, they're surrounded by water molecules. And they just keep doing that as long as there's room in the solution. They keep doing that until all the ions have been removed from the crystal and the crystal disappears into the solution. And that's what we're trying to show here with this hydration of the ions surrounded by water molecules. Now, water is not the only molecule that has a polarity to it. In this case, when we try to dissolve ionic solids, the solids break apart into individual ions, okay? But if we try to dissolve a solute that's not ionic, then the success of the solution, formation of the solution, depends upon whether or not the non-ionic molecule is also polar. And our example here is ethanol, right? Ethanol looks like this: 2 carbons, some hydrogens, and then 2 more hydrogens, and then an oxygen with a hydrogen on it. So what that does is it allows, just like water, this bond becomes polar, right? So you have a slightly negative side here and a slightly positive side there. And that's where the water molecules attack the ethanol molecule, so that you will have water molecules like this with a slightly negative, forms an electrostatic attraction there. And that allows the polar molecule to be drawn into solution. All right. This is a structure for table sugar, right? The same sugar that you put in your tea in the morning or your coffee. And you'll notice that this molecule is surrounded by OH groups. Everywhere it's got OH groups bound here like that. So it's got all these polar side groups that can be attacked by water. That's why so much of sugar will go into solution. A huge amount of sugar will go into solution because of these polar OH bonds. Now, these solutes are soluble in water because of their polarity or their ionic character, so that water can form these electrostatic attractions. But if you're attempting to put a solute in aqueous solution that is nonpolar, you don't get those interactions. Those electrostatic interactions are not strong enough to draw that material into solution. That solute will not dissolve. And oil is a perfect example. Oil has no polar bonds anywhere. So there's no potential for forming those electrostatic attractions that we've demonstrated for ionic and polar molecules. Right? So nonpolar oil does not dissolve in water. Now there's a theory behind how solutions form. I don't have a slide on it. This is an oversimplified slide here, so I'm going to draw it on the board. So you have a solute that you want to put in solution, and you have a solvent, and you want to end up with a solution down here. Okay? So what has to happen? And remember, nature just does what it does. And this is a way that we try to rationalize. We try to theorize what's happening. Right? This is an oversimplification, but it helps us understand what's actually happening at the microscopic level. So this first step, you have to add energy. To break bonds. In other words, you have to put enough energy in to break the bonds that are holding parts of the solute together. So for a sodium chloride crystal, those would be ionic bonds between sodium and chloride. There has to be enough energy to pull those sodium and chloride ions apart. Okay. So we have to expend some energy to do that. For the solvent, we have to add energy. To also break bonds. In other words, we've got to pull the solvent molecules apart by adding energy, and that process is often called make a whole. That is, create a space for the solute to enter, make a whole. So we add energy to the solute, we add energy to the solvent. Then once those are separate entities and we have a space for them, then we can get an interaction between the solute and the solvent molecules or ions, right? And for the solution, the formation of the solution, then this gives up energy. Because as the solute parts and the solvent parts come together, they're more stable. And stability is lower energy. So they give up some of that energy that was put in here and put in there. So we get energy back to form the solution. Now there's a balance here. The energy that we put in here, and the energy we get back here, we add those together, and that's the overall change in energy for the solution, the system. And that difference between this energy going in and this energy coming out determines whether the formation of the solution gets hot or the solution gets cold when formed. Now, here's a rule of thumb that we derive from what we've discussed so far, is like dissolves like. What that means is polar solvents more readily dissolve polar solutes, and nonpolar solvents more readily dissolve nonpolar solutes. And it's all based upon this interaction. But in this course, we're not going to go into any more detail than that. Like dissolves like is a good rule of thumb. All right. So let's check ourselves here. Which of the following solutes will generally not dissolve in the specified solvent? Okay, choose the best answer. Which will not dissolve? Okay, this requires some knowledge about the molecules involved. So when we're looking at the individual possibilities, we've got carbon tetrachloride mixed in water. So this is the solute column. This is the solvent column. So the solute for A is carbon tetrachloride, and the solvent is water. Right? For the second one, we have ammonia and water. For the third one, we have methanol. Right? That's the kind of alcohol that you drink it and you go blind. And water. And then nitrogen and methane. Okay. Carbon tetrachloride is pure carbon tetrachloride is a liquid. Ammonia is gas. Methanol is liquid. And nitrogen is a gas. And these are at standard temperatures and pressures. Liquid, 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 and a gas. Okay. The first one, this carbon tetrachloride is we're trying to dissolve it in water. Water is polar. And this is nonpolar. Methane is shaped like a tetrahedron. In other words, we've got a triangular base and then like that. So carbon's in the middle and hydrogen is at each of these apexes. That means it's symmetrical, and any polarity of the bonds, which is, they're very little, but any polarity is canceled out by the fact that they're all pointing in perfectly symmetrical directions. So that's nonpolar. Nitrogen is nonpolar because you've got two identical atoms and they pull equally on the electrons, so there's no uneven distribution. This is nonpolar. This is polar because of that OH group that we studied before. So this is polar. Ammonia is polar because it is like this tetrahedron here, nitrogen in the middle, hydrogen here, here, and there's one in the back. And then up here we have a pair of electrons. So this is unbalanced. This is the negative side, and these are the positive sides. So ammonia is polar. Carbon tetrachloride is like methane. Instead of hydrogen here, we have chlorines. So this is nonpolar. All right. Now, which ones of these will form solutions? Well, polar and polar means solution. That's good. Polar and polar means solution. Nonpolar, nonpolar means solution, like dissolves like. There's also another characteristic of gases. Gases always form solutions. Homogeneous mixtures are always the product of mixing gases. The reason for that is, even if they're polar and nonpolar mixtures, because there's lots of room, right? Gases have molecules that are very far apart. There's very weak interactions among the particles of a gas anyway. There's lots of room in there. They're big holes. So gases always form solutions. So not just nonpolar, but gas and gas forms a solution. So this nonpolar and polar does not form a solution. Carbon tetrachloride would not dissolve in water. All right. All right. We talked about solubility before and what the definition of solubility, how much of a solute will actually go into a certain amount of solvent. There are qualitative or semi-quantitative terms that help us deal with these variable amounts of solute in a solution, because mixtures, homogeneous or heterogeneous, doesn't matter. Mixtures do not change the identity of the solute and solvents or the mixture components. They still retain their chemical identity. So that means you can have a small amount of a solute in solution or in the mixture, or you can have a large amount. So the composition is variable. And we want to start to get a handle on expressing that variability. Okay, so one of the descriptive terms for a solution that has reached its solubility limit. In other words, you can't put any more solute in the solution. We call that solution saturated. It has a maximum amount of solute in the solution. That's saturated. If there's anything less than that, we say that the solution is unsaturated. That means there's still some room to add some solute if you so desire. And this, remember, happens at a given temperature. If you change the temperature, then you change that value. Under some circumstances, we can exceed what we consider to be the saturation level of solute in the solvent. And we call that supersaturated. As a practical matter, obtaining a supersaturated solution requires that you increase the temperature so that you can put more of the solute into the solution, and then you allow it to cool very gradually and without disturbance, because supersaturated solutions are what they call metastable. That is, they're stable, sort of. But if you disturb them in any way, then they'll revert to their saturated concentration, and any excess will drop out of solution. So a supersaturated solution is very unstable. And all you have to do to, once it cools, the solution cools, all you have to do to cause the excess amount of solute to come out of solution is give it an excuse. Shake it, scratch the inside of the beaker with a sharp instrument. We'll do it. Add a small crystal of the solute to it, and that will trigger the reversion of the solution to a saturated state. All righty. All right, again, solutions are mixtures. That means the amount of solute per unit of solvent is variable. And what we want is now a quantitative way of expressing how much of the solute is in the solution. And there are several ways to do that, depending on what your need is. Well, we have some more qualitative terms. We say that the solution is concentrated if there's a large amount of solute in it, and that's relative to its solubility. And we say it's dilute when there's a very small amount of solute. But if we want to quantify the amount of solute in the solution, we can use different expressions. The first one is mass percent. And that's simply the mass of solute per mass of solution times 100. So these have to be in the same units. They can be grams, they can be kilograms, doesn't matter. But they have to be the same unit. Then times 100 converts it to percent. And we usually express this as some value, percent. And we say mass. That means the units of measure for the solute are in mass units, and the units of measure for the solution are in mass units. Mass. We have to do that because, remember, percent is a dimensionless number. Percent simply means parts per 100 parts. Right? Those parts could be mass, they could be mass volume, they could be volume. They could even be moles and moles. So we need to specify. That's the Achilles heel of expressing any concentration values in terms of percent, is the fact that percent is a dimensionless number unless you specify the dimensions. All right. Now, the advantage to expressing concentration in terms of mass is the value that you obtain for concentration does not change with temperature. Remember, mass doesn't change with temperature. Mass is mass everywhere in the universe, well, except for close to black holes and traveling at the speed of light, but we're not going to encounter those problems. So mass is the value of your concentration in mass percent is going to be constant no matter what the temperature is. That's the advantage of mass percent. Okay, so let's take this problem. What's the mass percent concentration of glucose in a solution made by dissolving 5.5 grams of glucose in what solution? 78.2 grams of water. Now, is that the total mass of the solution? No. The total mass of the solution is the solvent plus the solute. So that means we need that same mass down here. This is the total mass of the solution. This is glucose. Now times 100. And if we pull out our calculator and check our calculation, 78.2, and then divide, and then times 100, we get, let's see, how many we've only got two significant figures. So technically, we can only say 66%. But I suspect this slide is going to give us three significant figures. Well, no. Oops, my mistake. 6.6%. Let me check that again. 5.5 and then 78.2 and divide and 100 times. Yes, 6.6%. And that's mass. Excuse me. Glucose in aqueous solution. That would be the complete expression of what this solution is quantitatively and qualitatively. Another way of expressing concentration is called molarity. Big M equals molarity. Now, the way we define it is how many moles of solute are contained in a liter of solution. Okay, that's molarity. Now you can see right off the problem with molarity is it's sensitive to temperature because volume changes with temperature. But it's convenient for other reasons, because if you have a 1 molar solution, you know that there's 1 mole of solute per liter. So if you remove a half a liter, half of that, you know that you will also have 1/2 mole of solute. Huh? So it's very convenient for that. And this expression, moles per unit volume, is like any other equation. If you know 2 of these, you can solve for the third one. So if we know this one and this one, we can find that one. Or if we know this one and that one, we can find this one. Or if we know that one and that one, we can find this one. It's like any algebraic equation. Okay. So what 3 molar hydrogen chloride in solution is 6 moles of hydrogen chloride per 2 liters of solution would give you one possible outcome, but it could be 3 moles in 1 liter of solution, or it could be 1.5 moles in 500 milliliters, all the same molarity. Okay. So for this exercise, we have 1 mole of sugar, and I assume that's table sugar. We have 1 mole in how many liters? 125 milliliters. That's the wrong unit of measure. How many liters is 125 milliliters? That's equal to, move the decimal 3 places, 0.1250 liter. Okay. So remember, when you change the unit, when the unit gets bigger, the number gets smaller. That should help you check yourself for making the wrong move for the decimal. Or if you're insecure about that method, you can say 125 milliliters and then use dimensional analysis. Right? How many milliliters in a liter? Well, 1,000. Okay. Divide 1,000 into that, and you get this. You say either way works just fine. Okay, back to the problem. If we divide 1 by 0.125, we get 8, let's see, 3 significant figures, right? Yeah. That's 3, this is 4, so we use 3. 8.00 molar glucose in aqueous solution. Okay. There we go. That's the concentration in terms of molarity. How about this one? Okay. So we're given 500 grams of potassium phosphate, and we dissolve it in enough water to make 1.5 liters of solution. So we know 1.50 liter here, we're already given. But we don't know moles because we're given mass. But we're also given the name of the compound, potassium phosphate. This is why I insisted early in the semester that you learn how to write compounds. Because if you don't know how to write this compound, you cannot answer the question. Potassium phosphate. Phosphate is a polyatomic ion with a 3- charge. Potassium in this ionic compound is an alkali metal with a +1 charge. So that means we need 3. Okay. There's your compound. Now, how do you convert 500 grams to moles? Dimensional analysis. 500 grams. We want to end up with moles. So moles goes on top, grams on the bottom. And remember, when you have grams and moles in a quotient relationship, you're talking molar mass. So what's the molar mass of this compound? Well, 3 times potassium would be 39.10 times 3. This is grams per mole. Then 1 phosphorus, which is 30.97. And then 4 oxygens, 16. And you add those together. So 39.1 times 3, and then 30.97 added to that, and then 16 times 4 is 64. So I get 212.27 grams per mole. Divide that into 500. And I get 2.355. 2.355 moles. Okay, we got 4 significant figures, 4 here, but we only got 3 here. Now we can solve the problem for molarity because we have moles in liters. So let's divide that by 1.5. And I get 3 significant figures, 1.57 molar potassium phosphate in aqueous solution. There we go. And there's the solution to the problem. 1.57 molar. Okay. Got another problem. Say you've got a 10 molar solution of sugar. What volume of this solution do you need in order to possess 2 moles of sugar? All right, well, in that case, we have 10 molar here. Right? And we want 2 moles of sugar. The unknown is the volume. So we solve for volume. Volume equals 2 moles divided by 10 molar, which is moles per liter. That means moles cancel. The denominator of the denominator is the numerator. So this comes up here, and 2 divided by 10 is 0.2 liters. Here we go. 0.2 liters. How many milliliters is that? Well, if the units get smaller by a factor of 1,000, then the number has to get bigger by a factor of 1,000, which means 1, 2, 3, 200 milliliters. Okay. All right. Let's see. I'm going to need some more room, so I'm going to erase this. There we go. Okay. For this exercise, you've got 2 separate solutions of sodium hydroxide and potassium chloride. And you're making each solution by dissolving 100 grams of each in separate solutions, but each is brought to a total volume of 250 milliliters. What's the molarity of each solution? First of all, do you expect them to be the same molarity? How would they be the same molarity? The only way they can be the same molarity, because you've got equal masses and equal volumes, is if the molar mass of sodium hydroxide and potassium chloride were exactly equal. Then that mass, 100 grams, would give you the same moles. But that's not the case. We've got sodium hydroxide and potassium chloride, and we want to convert 100 grams to moles. Okay, 100 grams So what we need is the molar mass of each one. Sodium hydroxide. Sodium's 23.00 grams per mole. Oxygen 16. And hydrogen is 1.01. So that's 10. That's 10. That's 40.01 grams per mole. Potassium chloride is 39.1 for potassium. Chlorine is 35.45. So that's 5, 5, 4, 74.55. Here we go. So now we can convert 100 grams of each compound to moles. 100 divided by 40.01 is 2.499. Okay. And 100 divided by 74.55 is 1.341. Okay, so if we're going to calculate the molarity, we need moles And what's the total volume? 250 milliliters. That's not liters. That's milliliters. So how many liters is 250 milliliters? Move the decimal to the left 3 places. 0.2500. And I get, let's see, we're rounding off to 4 decimal places. 9.998 molar. And for the next one, we have molarity equals 1.341 mole per 0.2500 liters. And that's 5.366 molar. So we have the same masses of these two compounds, but we have different molarities. They rounded off to 3 for sodium hydroxide. For potassium chloride, probably rounded off to 3 also. 5.37. So the moral of this story is molarity is an expression of numbers of solute molecules or whatever, ions per unit volume, not mass. Okay. All right. So let's see what we got here. You have 2 hydrogen chloride solutions. Well, if they're aqueous, that's hydrochloric acid. Solution A and solution B. Solution A has a greater concentration than solution B. Which of the following statements are true? So we've got 2 solutions, A and B. They're made of hydrogen chloride. And A is a greater concentration. So let's use molarity for convenience. The molarity of A is greater than the molarity of B. Okay? Now, we need more information. Which of the following are true? Okay? A, B, C, and D. If you have equal volumes of both solutions, solution B must contain more moles than hydrogen chloride. Well, what does this mean? This means moles of A per volume of A. This is moles of B per volume of B, correct? Okay. If you have equal volumes, if the volumes are equal, then how do you get this one to be more concentrated than that one? The only way, if the volumes are equal, the only way is to have more moles of A than B. So if you have equal volumes, solution B must contain more moles. No, it's the other way around. That one is wrong. The B says if you have equal moles of hydrogen chloride. So if you have equal moles of hydrogen chloride, what's the relationship of the volumes? Well, if the moles are equal, then the only way that you can make this one bigger is for the volume of A to be less than the volume of B. Right? That's how quotients work. So if B says if you have equal moles of HCl in both solutions, solution B must have a greater volume. Yes, That's true. How about C? Okay. C says to obtain equal concentrations of both solutions, you must add a certain amount of water to solution B. If the concentration is already less and you add more volume, you're making the concentration more dilute. So that will not make the solutions equal in molarity. And D says adding more moles of HCl to both solutions will make them less concentrated. If you add more moles of either one, it makes the solution more concentrated. So the only one that's true is B. All right. Problem solved. By the way, the best way to learn how to solve these problems is to get the review document that I give you in Brightspace and work those problems. Repetition, different scenarios causes your mind to be more flexible and solve problems easier. So I don't give you those review problems just because I like to write problems and I like to solve problems, which is the case, but for your benefit, work as many problems as you can. The more problems you work, the more comfortable you will become with chemistry at any level. All right. So we mentioned earlier, when ionic solids are put into solution, the ionic solid breaks apart into cations and anions. So if we have a solution that is 0.25 molar in calcium chloride, what's the concentration? Now that's the formula unit, CaCl2. But we know in solution, they're separate ions. That's the only way that they can exist in solution at this level. So the concentration of calcium then is the same, because there's only one for each one of these, one calcium for each. But we've got two chlorines, so when they go into solution, the chloride concentration doubles. All right. Now, by the way, what's the total ionic concentration in this solution? It's the summation. So you have 0.75 molar ions. Now, why is that important? Well, if you're like most of my students, you're going into the health professions. It's important to understand the relationship of a solution that you may be wanting to intravenously give to a patient, the relationship of that solution concentration to the concentration of solids in their plasma, in their body fluids. Because if you put something in there that's too concentrated, that's called hypertonic, and put something in there that's not concentrated, not as concentrated as their tissues, that's hypotonic, and either one has adverse impact on your patient. Now, for demonstration purposes, an isotonic solution of sodium chloride, right, in aqueous solution is 0.9%. And that's mass per unit volume. Now you'd have to take that and calculate what that equals in terms of molarity. But you could go the other direction and take this one and say, all right, how does it compare? But it's important for the health of your patient to understand this concept. Which one contains the greater number of ions? All right. This is one of those problems where I like to invoke the assembly line, which was popularized by Henry Ford. So A, B, C, and D, which just means that I'm going to solve this problem by doing the same thing over and over several times. So we've got 400 mils of that solution, 300, 200, 800, 300, 200, and 800 milliliters of each one of these solutions. And the first is 0.1 molar sodium chloride. The second one is, oh, they're all 0.1 molar. Calcium chloride, iron 3 chloride, and sucrose. 0.1 molar. Yep. 0.1 molar. And this is 0.1 molar. Okay, the question is, which one has the greatest number of ions? So what we need is to reconfigure our equation to solve for that term. That means N equals molarity times volume. I'm going to show you a little trick. If we're just comparing total amount of ions, we don't need to change this value to liters. Because if you multiply molarity times volume, and the volume is in milliliters, the result is millimolar, millimoles. So a tenth of that is 40. And a tenth of that is 30. Oops. What's wrong with this picture? This is millimoles of the compound. Right? So this is 20. And this is 80. What's the problem here? Sucrose doesn't make ions. So we don't need that one. We'll focus on these. Okay, now we have to convert to the number of ions. That's the millimoles of compound. We want to convert to ions. So we want to cancel compound. And that will leave us with ions. So what's the relationship here? Well, for every one compound, how many ions do you have? In this case, we have 2. In this case, we have 1, 2, 3. In this case, we have 1, 2, 3, 4. So the compounds cancel, leave us with ions. So 2 times 40 is 80 millimole of ions. And 30 times 3 is 90. And 20 times 4 is 80. So which one has the most number of ions? This one right here. Okay. Okay. Now, in this slide, I did change the volumes to liters. And that's technically what you need to do to find the number of moles. But we were just comparing to find the most. So millimoles work just fine. All right, that's just problem solution techniques. Let me see where we are. 15.4. Okay. I might run out of time, which means I'll go over time just a little bit. But we're going to get it done. I think it's better if I do it in one lecture. That way, next time we meet, I can start the review. So a solution with the greatest number of ions is not necessarily the one which has the largest volume or the largest concentration. So what's a standard solution? A standard solution is a solution that you prepare to very accurate values. In other words, you try to get as close as you can to the desired value of concentration. So if I wanted a 0.25 molar solution, then I would try to produce as close as possible. If this were in 1 liter, I would try to produce as close as I can to 0.25 moles of the solute with my measuring devices. That would be considered a standard solution. Okay, we got a little video here on preparing standard solutions. I'll comment on it afterwards.
Hi, I'm Jared Hyman, an assistant professor of chemistry at Elon University. Today, I'll be taking you through the appropriate technique and procedure for preparing a chemical solution. One of the most important abilities at all levels of chemistry is the preparing of a solution of a specific concentration. First, we'll define some of the terms used in this process. A solution is a homogeneous mixture of 2 or more chemicals. For the simplest solution, a smaller amount of one chemical, called the solute, is placed in a larger amount of a second chemical, known as the solvent. Today, we will be preparing a solution of sodium chloride, using a small amount of sodium chloride as our solute, added to a larger volume of water, our solvent. Before beginning any experiment, it's important to observe appropriate lab safety procedure and know the hazards of any chemicals you're working with. In any chemical reaction, it's important to keep track of the exact amount of reactants present, and for stoichiometric purposes, we use the term mole to define the amount of a substance. A mole is a counting term, similar to a dozen eggs, where 1 mole is equal to 6.022 times 10 to the 23rd things. As you can see, this is a really large number. The periodic table uses molar counting as a means of converting to a more experimental term of mass. For example, 1 mole of carbon atoms has a mass of 12.01 grams. In a compound such as sodium chloride, it's made up of 1 mole of sodium atoms with a mass of 22.98 grams per mole, along with 1 mole of chlorine atoms with a mass of 35.45 grams per mole, giving us a total of 58.43 grams per mole of sodium chloride. This means of using mass to determine the amount of a substance is useful for pure chemicals. But in the case of solutions, we now have a mixture of multiple different substances. Therefore, we express amount as a concentration. The most common unit for concentration in chemistry is molarity, abbreviated capital M, which indicates the number of moles of solute dissolved in a certain volume of the total solution. This gives molarity derived units of moles per liter. It is very important to note that this is a volume of solution, not the volume of solvent. Today, we will be preparing 500 milliliters of a 0.25 molar sodium chloride solution. Before beginning, it's important to map out your procedure for preparing this solution. Here, we'll look at the amount of sodium chloride we need in this solution. We know that we want to prepare a 0.25 molar solution, which means that there is 0.25 moles per liter of solution. We also know that we only want 500 milliliters of this solution, or a half liter. If we multiply these two terms together, we can see that we will need 0.125 moles of sodium chloride. From earlier, we can remember that there are 58.43 grams per mole of sodium chloride. We can determine that the exact mass that must be measured out is 7.304 grams of sodium chloride. In lab, obtain some sodium chloride in a clean lab scoop and using a balance with some weighing paper, measure out as close to 7.304 grams as possible, marking down your exact mass. Note that if you go over the desired mass, it's never appropriate laboratory procedure to put the excess reagent back into the original container. Always use an additional container to collect the excess. Once you've measured out your solid and recorded the exact mass, transfer all of the solid to the appropriate sized volumetric flask. Volumetric flasks are made specifically for this purpose and should be used over other less accurate labware, such as beakers, Erlenmeyer flasks, or graduated cylinders. Here, we just transferred our solute to the 500 milliliter volumetric flask. If any solute remains on the weighing paper, use a spatula or a small amount of water to transfer the remaining salt. Next, add enough water so that the bulb area at the bottom of the flask is approximately half full. This will give you enough room to swirl the liquid, allowing the solute to completely dissolve. Again, it's critical that all of the solute is dissolved prior to filling to the appropriate volume, as different solutes may take up more volume in solution than their undissolved salts. Now that the sodium chloride is completely dissolved, we can fill the rest of the bulb area and some of the neck with water. You should now carefully and slowly add water, our solvent, as it begins to fill the neck. Once you approach the etched or printed line on the neck of the flask, you should add solvent dropwise, monitoring the location of the meniscus. Water, as a polar solvent, tends to cling to the glass walls of a flask. This phenomenon creates what is called a meniscus. The bottom of this curved meniscus should sit directly level with the line on the flask. At this point, there is exactly 500 milliliters of solution with an air of 0.2 milliliters. Different volume flasks have different air values. However, the air on a volumetric flask is much lower than any other type of glassware of similar volume. For example, the volume markings on a beaker or an Erlenmeyer flask are only accurate to plus or minus 5%, meaning if the meniscus were on the 500 milliliter line, it could be anywhere between 475 milliliters and 525 milliliters. On the other hand, using a volumetric flask, we know that the volume is exactly somewhere between 499.8 milliliters and 500.2 milliliters, meaning it's much more accurate. We now must determine the exact concentration of our solution by taking the mass that we measured out and dividing by formula mass for sodium chloride, 58.43 grams per mole, which gives us a total number of moles in our solution of 0.1253 moles. We can then take this number and divide by our volume of 0.5 0.000 liters to give us a total exact concentration of this solution of 0.2501 molar sodium chloride. This value and the contents of the solution should be clearly labeled on the chosen storage container for laboratory safety protocol. You've now learned how to make a solution from a solid. Everything you need to do this demonstration in your lab is available from Carolina. We have experts who can assist you with any of your science demonstration needs. Visit us at carolinachemistry.com to see our complete line of products and kits for chemistry.
So, I was watching this video for mistakes, and this particular video only had one mistake, and that was on the board, the value for liters, the volume, was given with an orphan decimal. That is, the decimal was not preceded by a zero. The rest of the procedure was accurate and useful. Okay, that's how you prepare a standard solution. In this case, it's an aqueous solution. All right. So there was some mention that you wanted to put some water in the volumetric flask and dissolve the solid completely before you continue. Two reasons for that. You don't want anything that's not in solution when you finally reach the total volume. And secondly, when you put solids in solution, sometimes they get hotter, sometimes they get colder, which means that the temperature is going to be a factor in the measurement of volume. Now, these flasks are calibrated to give you that exact volume, plus or minus a small amount, at a given temperature. And that temperature is usually 25 degrees Celsius. So if your solution gets colder, then the volume is going to be your desired. Once you reach your volume, it should be less than the line says. And if it's hotter, it should be greater than the line says. Now, which one would you prefer? Well, if it's hotter, then and you put it on the mark, then as it cools, the level is going to drop. That can be corrected simply by adding a little more water once you've reached 25 degrees Celsius. But if it gets colder and you set it on, you dilute to the volume mark, then as it heats up, the volume is going to increase. And now you're stuck. You've got too much volume. So what you want to do is dissolve everything with some water and then make sure it's dissolved and then set it aside until the flask and its contents reach room temperature, which is usually in the neighborhood of 25 degrees, between 20 and 25, which won't be a significant problem for your volume and the concentration of your solution. And then once it's reached that temperature, you can finish bringing the volume to the mark. So we talked about some things that could go wrong. You could make an error in measuring the mass, or you could make an error in transferring the mass from the weighing container into your flask. You could try to dilute it before everything is dissolved. Incomplete dissolution will introduce error. You could read the volume mark wrong. In other words, if you have the neck of the flask here, and you got a mark right there, right? And you want the volume to be, the meniscus to be right there, like that. Then if you position your eye up here, you're going to introduce error. Or if you position your eye down here, you're going to introduce error. In other words, the position of your eye introduces what's known as parallax error. You want your eye to be exactly level with that mark. And I've already mentioned this possible problem. If the mixing, the creation of the solution is exothermic, that means it's going to get hot. If it's endothermic, that means it's going to get cold, and that influences your concentration. There could be other possible errors that you could introduce. Now, what do we mean by dilution? Dilution starts with a concentrated solution. So you have molarity that's relatively concentrated compared to the final concentration that you have as your target. So you want to end up with a more diluted solution. How do you do that? Well, you could do it by changing the amount of solute, but that's pretty difficult once the solution's already made. So we change the volume by we change the concentration by changing the volume. This is equal to moles per unit volume, and this is equal to moles per unit volume. So if we have a value here and we increase the volume term, we decrease the concentration. And that will get us to this place, the diluted concentration. When you multiply, say you have a container with concentrated solution here, and you want to dilute it in such a way that you reach a diluted concentration. Okay, how do you do that? Well, you only take a portion out of this one. And that gives you a certain number of moles. The moles of the concentrated side equals the concentration times the volume that you take out. So you take out a certain volume. Take out a certain volume here, and you put it in there, and then you add some more solvent. Now, what factor did not change in this process? The factor that did not change is once you get this volume here of the diluted times that one, that's equal to the number of moles of the diluted one. But this one is the number of moles. When you take a certain volume out of here, what comes out of here? The number of moles there. What goes in here? The number of moles there. These two are equal. The same number of moles you take out is the number of moles you put in. So if that's equal, then when you dilute this number of moles to a greater volume, you're decreasing the concentration. You're decreasing the molarity. So if this is true, and that's true, and this is true, and this is equal to the diluted molarity times the volume of the dilute, and this is equal to the concentrated molarity times the concentrated volume. Remember that old that math identity. If A is equal to B and B is equal to C, then A is equal to C. So if these two are equal, then these two are equal. So the molarity of the concentrated times the volume of the concentrated equals the molarity of the dilute times the volume of the dilute. That's your dilution equation. Right there. And in this expression, it's M1V1 equals M2V2, which is perfectly valid. But this is in relationship to the description I just gave you. Okay, we're going to get another video of how to do the dilution, and there are several mistakes in here that I'm going to call your attention to afterwards.
Hi, I'm Jared Hyman, an assistant professor of chemistry at Elon University. Today I'll be taking you through the appropriate procedure and technique for diluting a solution. A common laboratory technique is preparing a more dilute solution from a concentrated stock solution. In this case, we are going to prepare a 0.250 liter solution of 0.01 molar. We know our stock solution has a concentration of 0.250 molar. The first thing we need to do is determine the exact number of moles in our dilute solution. We know our concentration needs to be 0.01 molar or 0.01 moles per liter. Since we know our number of moles per liter and we know the volume we need, we can calculate that we need exactly 0.0025 moles of sodium chloride. Knowing our stock solution contains 0.25 moles per liter, we can take the number of moles needed in our dilute solution and divide by the concentration of our stock solution to calculate the exact number of milliliters that must be transferred into our new solution. In this case, 0.01 liters of sodium chloride solution, or 10 milliliters. This is the stock solution of sodium chloride that we will be diluting. Make sure to pour the stock solution into another container before inserting the pipette into the solution. This is because you do not want to contaminate your stock solution. In this case, I'm using an Erlenmeyer flask. Notice that I have clearly labeled the flasks to adhere to proper laboratory safety protocol. To prepare our dilute solution, we will take a 10 milliliter aliquot of our stock solution using a 10 milliliter volumetric pipette. To use the pipette, place the pipette in the liquid to be collected. Squeeze the pipette bulb and allow the liquid to rise up the pipette. You should allow the liquid to pass the line marked on the pipette, but before the bulb. Remove the bulb and place your other thumb over the end, creating a seal, and slowly release just the corner of your thumb, allowing the liquid to exit so that the meniscus is directly on the line marked on the pipette. This takes some practice, and you may need to use the bulb to pull more liquid into the pipette again. Never pipette by mouth. Once you have the exact amount of liquid required in the pipette, hold your thumb firmly over the end and transfer the pipette to a new volumetric flask, in this case a clean 250 milliliter volumetric flask. Allow all of the liquid to flow out of the pipette. Do not use the bulb to force the liquid out, as pipettes are designed to deliver the exact amount of liquid, and there may be a small amount of liquid remaining at the end. Remove the pipette and follow the same procedure as before, filling the volumetric flask with solvent, again monitoring the meniscus until the exact volume is reached. You've now learned how to prepare a dilute solution from a stock solution. To see how to prepare a stock solution, you can view our solution preparation video at carolina.com/video. Everything you need to perform this technique in your lab is available from Carolina. Visit us at carolinachemistry.com to see our complete line of products and kits for chemistry.
All right. So the only big mistake I saw in that video was when the pipette was pulled out of the solution, it was immediately brought over to be dispensed into the volumetric flask. The problem with that is these pipettes, the tips, right? The tips can have solution clinging to the outside. That's not part of the measured value. So if you bring it over, you're adding extra. So there are two ways to handle this. The way our demonstrator did it, plus wipe your tip of the pipette with a chem wipe. The other way is when you are drawing up the solution, you draw up the solution and you have your bulb here, and then you have this part with the line on it. When you have solution up here, pull it out and wipe the tip. Then allow this to drain down to the mark, and then you might have a little bit on the outside. Then you take the tip and you touch it to the inside of the stock container, in this case, the Erlenmeyer flask, and that will draw this bead away from the tip. Then you can take it and deliver it into your volumetric flask. And he was correct about one thing. Let this drain against gravity. These volumetric pieces, these pipettes, are calibrated to drain at a certain rate with aqueous solutions. And then when they get down to a certain point, there's a force that's keeping some of that solution in the tip. So the volumetric, the pipette is calibrated to account for that leftover. And when you do that, touch the tip to the inside of the glass to pick up anything that's left on the tip. That is an accurate delivery of the volume as calibrated by the pipette. Okay. So here's it's just a slide on dilution, and it doesn't go into any great detail, except for when you mix, you want to be, you want to add solution and then mix before you bring it up that final amount to the mark. Okay. All right, 0.5 molar solution of sodium chloride in an open beaker sits on a lab bench. Which of the following would decrease the concentration of salt solution? Decrease the concentration. If you add solvent, you will decrease the concentration. So that first one is correct. If you pour some of the solution down the drain, you're pouring a proportional amount of solvent and solute. So that has no effect on the concentration. If you add more sodium chloride, you're actually increasing the concentration of solute. Right? If you let the solution sit out on the open bench for a couple of days, assuming, well, in this case, sodium chloride is not volatile, so the only thing that evaporates is the solvent, and you're increasing the concentration. So at least two of these, no, just one. Only A will decrease the concentration of the salt solution. All right, here's a problem. What's the minimum volume of 2 molar sodium hydroxide solution needed to make 150 milliliters of 0.8 molar sodium hydroxide solution? All right, we're going to use this equation. Concentrated, volume concentrated, molarity dilute, volume dilute. But it's absolutely essential that you get those numbers in the right place in this formula. Otherwise, you'll get the wrong calculation. So that's why I like to set up a table. Molarity, volume. This is dilute, concentrated. And I take the word problem and I extract the information from it. What's the concentrated molarity? 2.0. What's the dilute molarity? 0.8. What's the concentrated volume? We don't know. That's the question. What's the final volume of the dilute? 150 milliliters. Okay. So now we can put those terms in the right place. I'll also preface this calculation by saying, since this is essentially a ratio, you can use the same volume units here that you're given. If you understand that the answer is going to come out in those same units. So we can do this, we can solve for that one first. So that final volume is going to be the diluted divided by the molarity of the concentrated. So now we can put those values in here. 0.800 molar and diluted volume is 150 milliliters divided by the concentrated, which is 2.00 molar. Notice that the molarities cancel and the volume now is going to be in milliliters. So we set the problem up and our answer is 60 milliliters. Okay. Now, if you're actually doing a calculation of molarity with the simple formula, the volume must be in liters. But when you're using a ratio like this, you can use any volume that you want, whatever you're given, as long as you understand that the answer is going to come out in those same units. Okay. All right, now we're going to talk about stoichiometry in the time remaining. Remember, when we have a stoichiometry problem, first thing you need is a balanced equation. All right. The second thing you need is moles. Remember, when you have a balanced equation, you cannot move anywhere in that equation unless you have moles. When we had mass as a given quantities, we converted mass to moles using molar mass for each of the compounds. When you have solutions, you've got to calculate moles from solution concentration and volume. Molarity times volume equals moles. Okay. Then if you have absolute amounts of two or more reactants, you've got to decide which one is limiting. The limiting reactants. And then you answer the question. The question could be anything. So that takes you off in different directions. Then it depends on what the answer requires. Does the answer require mass in the end, or does it require a number of moles simply, or does it need you to calculate the new concentration? Whatever's required. Okay, here's an example. let's take this example and work the problem. 10 milliliters of 0.3 molar sodium phosphate in solution, and we assume that these are aqueous solutions, reacts with 20 milliliters of 0.2 molar lead-2 nitrate solution. Assume no volume change. We have to do that, otherwise the concentrations don't work. Because we've got two solutions that we're going to combine, and they're going to react. All right, we do need to know what precipitate forms. We talked about that in the past, of course. And then what mass of precipitate will form is the question. Okay, so the first thing we want to do is write the compounds. And put them in an equation. I think that would be simpler than just going straight to the answer. So let's say we've got sodium phosphate. Aqueous solution. Plus lead-2 nitrate. In aqueous solution. And that produces what? Well, this is a double replacement reaction. Lead reacts with phosphate, sodium with nitrate. As it turns out, lead-2 phosphate is the consequence. We have 3 here and a 2 there. This is a solid. And what we have left over is sodium nitrate in aqueous solution. Okay. So the precipitate that forms is lead-2 phosphate. There we go. Lead-2 phosphate. What's the mass of the precipitate? Now we have to make a balanced equation. Right? These types of equations usually are very well behaved. So if we need 3 leads on this side, we put a 3 here. But now we have 6 nitrates. Now we need 6 sodiums. So that's 2 times 3 is 6. 2 phosphates here, 2 phosphates there. We're balanced with a 2, 3, 1, and 6. Now you can use the budget method. That's perfectly legitimate. But with these types of equations, it's much simpler to do it just the way I did. Okay, what's the limiting reactant? Well, let's put what we know up here. 10 milliliters of 0.3 molar sodium phosphate. 10 milliliters of 0.3 molar. Okay, and the other is 20 milliliters of 0.2 molar. 20 milliliters of 0.2 molar. Okay. Now, the way the slide is set up, I changed the volume to liters. And that's fine, but we can work with millimoles just as easily. Well, actually, we're probably going to have to change the moles eventually, but we can do that afterwards. So 0.3 times 10 is 3 moles. And 0.2 is 4. Actually, millimoles, excuse me. Millimoles. Okay. So let's go ahead and change it to moles. So we need to move the decimal place 3 to the left, 0.0030 0 moles of sodium phosphate. And this one I'm going to put down here is 0.00400 moles. Okay. Now we want to change. We want to calculate how many moles of lead-2 phosphate are produced from this reaction. If all of this is converted, then the ratio between sodium phosphate and lead 2 phosphate is 1 here and 2 there. Right? So that's 0.00150 moles of lead 2 phosphate. Okay. We do the same thing for this one. We want to convert lead nitrate to lead 2 phosphate. And that's again 1, and this is 3. So 3 divided into 4 is 1 1/3, or 0.00133 moles of lead phosphate. Okay, so this one is the limiting reactant, the nitrate. And that's what these calculations are supposed to show us. There we go. So now we can use the limiting reactant to calculate the mass of this precipitate. Now we already have the moles. We need the molar mass of that compound. So we can say it's 3 times lead, which is 207.21. And 2 times phosphate, which is 3097. And 8 times oxygen. Okay. So 207.21 times 3 and 30.97 times 2, and then 8 times 16. And together is 811.57. So we can convert this to grams, because moles cancel, and 811.57 times 0.00133 is 1.079 grams of lead 2 phosphate. That's on the next slide. Well, they rounded it off to 3 places. That's fine. Okay. Now, using this same scenario, what's the concentration of nitrate ions that's in solution? Well, notice that the nitrates are the same number of moles of nitrate are in solution as we started with. So the moles of nitrate here, the moles of nitrate, this would be the moles of lead nitrate. And for every one of these, you get 2 nitrates. So that means we have 0.00800 moles of nitrate ions. What's the volume? Well, the volume is 10 plus 20, which is 30 milliliters. Right? 30 milliliters is 0.0300 liters. That will be the concentration of nitrate in solution after the reaction. Which is 0.267 molar nitrate ions. Okay. And that calculation should show up right here. Because it's a spectator, 0.27 rounded off. Now, the more difficult question is the next one. what's the concentration of phosphate ion left in solution? Notice that this is limiting. That means all of that lead is used up to make this compound. But this phosphate is excess. Right? So we're not going to use up all the phosphate. There's going to be some left over. How much is left over? Well, what did we use? Let's see. What's the simplest way? Here. 0.00133 moles of lead 2 phosphate was produced. Well, how many moles of phosphate were actually used? Well, the ratio is 2 to 1. We have 2 moles of phosphate for every 1 mole of compound. So 2 times that is going to be the amount of phosphate used. How much phosphate did we start with? Well, we started with 0.00300 moles of this compound, and there's one of these for every one of those. So we started with 0.0300. Excuse me. Let's start over again. 0.00300 moles of phosphate. Right? Because for every one of these, there's one of those. So this is what we started with. And what we used was 0.0266, or actually 267. Yeah. 0.00267. So we subtract those. 3 and 6 from 9 is 3. And is that right? Add these together. 0, 0. Yep. So this is the moles of phosphate remaining. So what's the final volume? The same as before. Right? 0.03 liters. So we divide this by 0.0300 liters. And that's 0.011 molar. It may give it to us in scientific notation. Okay. That's used up in the reaction. There. So they've already rounded it, so there's going to be some discrepancy. .01, right? So I calculated with greater accuracy than they did, but we're close. So that's what's left in solution of the phosphate. All right. We're over time, but I'm going to finish this lecture. Neutralization reactions. This was stoichiometry. Neutralization can be approached in a stoichiometric fashion also. In fact, that's usually the case. When we say neutralization, we're usually referring to an acid plus a base. And the neutralization of the acid, and we can represent the acid as HA. It's got a proton here, a hydrogen, and some other part of the molecule. And then usually the base has a hydroxyl on it. Not always, but in most cases, yes. And in this case, we have one proton here and we have one hydroxyl there. But it doesn't have to be that way. It can be a different ratio. We could have 2 there, we could have 2 here, whatever the case. But what we get is a double replacement reaction where this cation is associated with this anion. And it may be soluble. Or it might precipitate. We don't know without particulars. But this hydrogen plus this hydroxide makes water. So this is our acid. This is our base. And they always produce a salt. And this is a salt in chemical terms, not a salt in cooking terms. That's a chemical salt and water. Those are the results always of an acid-base reaction. That's the net ionic equation. If this is soluble, then these ions here cancel out with those. And what you get is OH, OH minus plus H plus is this one. That's the net ionic equation for a neutralization reaction, especially for a strong acid and a strong base. So let's say we're going to titrate, and titrate is a term that we use for this neutralization. We're adding a known amount of one, either the acid or the base, to a known amount of the other. And the objective is usually one of the components, either the acid or the base, is an unknown concentration. But the other component, the acid or the base, is a known concentration. So if we introduce a known concentration of one component and we know the volume, we can calculate the number of moles. And then if we deliver a volume that exactly matches the number of moles of hydrogen ions or hydroxyl ions, then we can back calculate and find out what the concentration of the unknown is. That's one of the main driving forces behind using this titration method. But here we have sulfuric acid plus sodium hydroxide. So what are we going to get from that? Sodium and sulfate. And this is soluble. Plus water. Okay. Now we balance the equation. We got two sodiums here, two there, so we need two here. Two hydroxyls and two hydrogens makes two water. Now the equation's balanced. What we're given is 1 liter of 0.5 molar sulfuric acid. 1 liter of 0.5 molar sulfuric acid. All right. How many moles of sulfuric acid is that? 0.5 moles of sulfuric acid. Okay. How many moles of sodium hydroxide are required? Exactly the same. Well, actually, the ratio here is 2 to 1. 2 sodium hydroxides for every 1 H2SO4. Why is that? That's because the molecule only has 1 hydroxyl. And this molecule has 2 hydrogens. Right? This one only needs 1 hydrogen to make water. So you actually need 2 of them to absorb those 2 hydrogens. So that means we need 1.00 moles of sodium hydroxide. There's a balanced equation, there's a conversion, and that's how many moles of sodium hydroxide are required. Now, if you do a lot of these in the course of your workday as say a lab technician, then there's an easier way to deal with it in which you don't need to know what the acid is or what the base is. You only need to know what their concentration is in terms of hydroxyls and hydrogens. So, and that's called the equivalent. So the equivalent for this one is not 0.5 moles, but it's 1.00 equivalents of hydrogen ions. Okay? And this one is 1.00 equivalents of hydroxyl. So there you have an equal amount. This is that many equivalents, this is that many equivalents, and they produce one equivalent of water. Now, the equivalent weight is to say what mass of this would give you one equivalent of hydrogen ions. Well, what's the molar mass of sulfuric acid? The molar mass of sulfuric acid is 32.07 and 2.02 for the hydrogens, and 4 oxygens is 64. So let's say 98 grams per mole. That is the mass that would give you a mole of those. But how many equivalents would that be? That would be 2 equivalents. So what mass would give you 1 equivalent? Half of this. Divide by the number of hydrogens. So that would be 49.45? No. 0.5. This will be grams per equivalent. That's the equivalent weight. Okay, so 49 for sulfuric acid. Now, if there's only 1 hydrogen per molecule, then the molar mass and the equivalent mass are exactly the same. Hydrochloric acid, nitric acid would be the same. Sulfuric acid would be half. Sodium hydroxide would be equivalent, would be the same. Potassium hydroxide would be the same. What about calcium hydroxide? It would be half the mass because there are 2 hydroxyls for every 1 molecule, or formula unit, I should say. Now that we know the equivalents, the number of equivalents, we have a new measure of concentration. The new measure of concentration is called normality. And it's given this large N. Normality. Normality is the number of equivalents per liter, right? So the normality of this solution would be 1 equivalent per liter, which would be 1 normal. If this were 0.5 molar equals 1 normal, because 1 liter supplies 1 liter of 0.5 molar supplies 1 equivalent of hydrogen ions. So once you know what the normality is, it doesn't matter what the acid is or the base. Once you know the normality, then that's irrelevant. Okay, if barium hydroxide is used as a base, how many equivalents of barium hydroxide are there in 4 moles of barium hydroxide? There are actually 8, because you've got 2 hydroxyls for every mole of barium hydroxide. And that's all she wrote.